I would like to introduce Jeffrey Zhang, who will be presenting BEIR, B-E-I-R, the best multicast solution for segment routing. Jeffrey is a distinguished engineer at Juniper Networks and is coming to us today from the Boston area. This is Jeffrey's second time presenting at NANOG. Jeffrey's first talk at NANOG was called Multicast and Segment Routing Networks at the virtual NANOG 81 in the year 2021. It talks about various multicast options for segment routing networks, and today he is going to have a deep dive on the best option, BEIR, B-E-I-R. Welcome, Jeffrey. Thank you.
Good afternoon, everyone. So let me just get started on my presentation. So just a recap on the previous presentation back in NANOG 81, Multicast in SR networks. We started with the principles of segment routing. And from those principles, we look at the options that we have for multicast. From there, we look at a list of options that we could consider in the order. The first one, if you care about efficient replication without having to maintain per flow or per tree state inside the network, and if most of your routers can support BEIR, then the best option is BEIR. And next to that, the traditional multicast, whether it's PIM or P2MP tunnel or ingress replication, it could also work very well for you, especially if you don't need a controller, and if you don't mind running those traditional protocols, PIM, MLDP, or RSVP, P2MP, in your SR network after you moved away from LDP or RSVP for unicast. But you can still run the multicast version for multicast purpose. And then finally, if you do need to use a controller for the tree calculation, or you want to use the controller to do the signaling to the tree nodes, or if you just want to get rid of those traditional protocols for whatever reason, yes, you can do controller signal the multicast. And there the options include tree seed or better known as SR-P2MP in IETF, or you can use the BGP signaled IP multicast, or BGP signaled MLDP tunnel from the controller. Just keep in mind that you still have the per tree, per tunnel state inside the network. So that's the recap of the previous presentation. At that time, we didn't talk about the BEIR. The reason for not talking about the best option at that time, it will become clear when we talk more about BEIR. So to start today, again, want to start with the state versus replication efficiency. We already talked about that with traditional multicast technologies. If you want to have efficient replication, then you need to maintain per tree states on the transit routers. Depending on different protocols you use, you set up different kind of tree states, whether it's IP multicast or it's MPLS multicast, and you can use PIM or MLDP or RSVP-TE. You can do all those. Alternatively, you can use ingress replication. With ingress replication, you do not maintain the per tree states in the core, in the transit routers, but then the replication is done at the ingress router. Obviously, that is not efficient. Now, BEIR is this new technology, I call it the technology wonder, that achieves both efficient replication and without incurring per tree state. Because of that, It is the ideal multicast solution for a segment routing network because the number one principle of segment routing is you do not maintain per flow state inside the network. And BIER does that exactly. Interestingly, BIER is actually independent of SR. It was developed on the side, and whether SR comes or not, the BIER can still be there and work for multicast. Because we do not maintain per tree state anymore, the scaling and convergence are only related to the network topology, not to the number of multicast flows or multicast tunnels anymore. So that's very good. And then there is no special use cases for BIER. Any multicast scenarios can benefit from this BIER technology. And especially in a scaled environment where you care about convergence, and then BIER is the best solution. So I've talked about BIER, the term so many times. What exactly it means? It's a short term for the bit indexed explicit replication. Basically, each packet will carry a bit string. Each bit in that bit string identifies an edge router that needs to receive that packet. The transit routers will look at that bit string, will figure out how it should replicate to the downstream neighbors. Because because of that bit string, each router knows where it needs to forward the traffic by consulting a forwarding table that is only related to the topology, not related to the number of flows or number of trees you have to maintain. These slides have quite some terminologies here. I will quickly go through them, but it's okay if you don't remember any of those. When we encounter those later, I will give some context and explain what those terms again. So first of all, BFR, BIER forwarding router. BFIR is ingress BFR. BFER, egress BFR. And BFR ID. Each ingress or egress BFR has a 16-bit ID number that basically maps to a bit in that bit string. And then BIER prefix is basically a loopback address on a BFR. BIRT is a BIER routing table, BIRFT, BIER forwarding table, BSL, bit string length. Now, FBM is a very important concept in the BIER technology. I will actually explain that later. I want to start with this very simple topology to explain how the BIER forwarding works. We have a network of 6 nodes here. A, E, F, D are the edge routers, and B and C are transit routers. Each of those edge routers have a BFR ID. In this case, D has 1, F has 2, E has 3, and A has 4. Each of those ID maps to a bit in this bit string, a 4-bit bit string. A sends a BIER packet to B with bit string 0111, meaning that this packet needs to be received by E, F, and D. Now B looks at that bit string, figures out that it needs to send 2 copies, one to C and one to E. The copy it is sent to C carries an updated bit string 0011 corresponding to F and D. Now, when the packet arrives C will in turn decide that a copy needs to be sent to F and another copy needs to be sent to D. Now, how this forwarding decision is made is based on this BIFT, BIER forwarding table. Here we have router B's bits here. It's actually very much similar to the unicast routing table, except that here the key of each route entry is not a prefix, but it's a ID. Here we have ID 1, 2, 3, 4 for each of those entries there. Each entry has BFR neighbor. Basically says that you need to send it to that particular neighbor. And next to it is the FBM. FBM is actually a property of the BFR neighbor. It represents all the BFERs that are reachable through that particular BFR neighbor. In this case, BFR neighbor C has a FBN 0011. What it means is that once you send a packet to C, both D and F are covered. So the FBM of neighbor C is obtained by doing a logical OR of the D and F's bit mask there. Here, D has BFR ID 1, so its bit mask is 001. And F has ID 2, so its bit mask is 0010. And you OR them together, you get C's FBM 0011. Again, meaning that if you send a copy to C, you will cover both D and F. So now look at this BIER forwarding table again. If you look at the second row, BFER ID is for router F. Here we are looking at the B's BIFT. So to reach F, you need to send a copy to C. But once you send a copy to C, you can cover both D and F. So that's the meaning of each entry here. These slides describe how the forwarding and lookup is done. But the text here is boring. I'm going to skip it. Just come to the next slide where we're going to look at the example how this forwarding is done. Again, simple topology with the corresponding BIFT on router B. Router A sends a packet to B with 0111, meaning it needs to reach EF and D. Now, what B does is that it checks the lowest bit that is set in the incoming bit string. In this case, the lowest bit that is set in the incoming bit string 0111 is the first rightmost bit. So it used this index 1 to look up the BIER forwarding table, and that gives you the first entry in the routing table and the BIER forwarding table. And it tells you that you have a BFR neighbor C and with a FBM 0011. So B will send a copy to C with the updated bit string 0011, which is the logical end of this incoming bit string and C's FBM. Now, it also updates the incoming packet's bit string to 0100, which is the logical end of the incoming bit string and the reverse of the neighbor C's FBM. That's because once we send a copy to C, that takes care of all the BFERs can be reached through C. So we only need to worry about the remaining bits that not covered by C. Therefore, we do that bit string, income bit string, and reverse of the C's FBM. Now, with the remaining bit string 0100, again we check the lowest bit that is set on the rightmost side. Now, the lowest set bit is the third bit. So we use number 3 to look up that BIER forwarding table. That gives us the third entry, and the BFR neighbor is E. So we send a copy to E. Again, with the updated bit string, and by doing the incoming bit string and the logical end of neighbor E's FBM. So that gives us 0100. That is the bit string that is in the copy that's sent to E. After that, we do a logical end of the incoming bit string and the reverse of E's FBN. Now we have no more bits left. Then this forwarding is done. So here we have a simple 4-bit bit string. In practical, typical bit string length is 256 bits. Now, no matter how many bits and which bits are set in that bit string, whether it's 256 or even 1024, no matter how many bits, no matter which bits are set, the number of lookup is bound by the number of replications that you need to do. It could be that all 256 bits are set in the incoming bit string, but if you only need to send one copy to one downstream neighbor, because all those 256 edge routers can be reached through their single downstream neighbor, then you only need to do one lookup. So that is makes it very efficient. It's a very smart algorithm here. Oh, we just talked about how B forwards the traffic, and then when C gets it, it does the same algorithm, send one copy to D and one copy to F. So we explained how BIER forwarding works. Now, we take one step back and just look at the entire BIER architecture. It has 3 layers. The very top is what we call multicast flow overlay. It is used by the edge routers to signal to each other, hey, I need to receive a packet for this multicast flow. It's done from the egress router to the ingress router. That's how here we look at this. We said that A sent the packet to B using that 0111 bit string. But how does A know that it needs to use 0111 instead of 0001? That's the job of the multicast flow overlay. Flow overlay let each BFIR, which is ingress BFR, to decide what bit string it needs to use. Examples of this flow overlay includes BGP MVPN, EVPN, or it could be PIM, even MLDP, or even IGMP. There are all kinds of flow overlays. And to those overlays, BIER can be considered as an underlay tunnel. The next is the BIER signaling and forwarding. We need to exchange some information among the BIER forwarding routers so that they can calculate those BIFs. So the routers do need to maintain the BIFs. They do maintain some states, but those states are not per tree states. They are just related to the network topology. And finally, the routing underlay. The packets, BIER packets, are routed in the routing underlay. In the simplest case, it's just the same as a unicast routing, but you could have different routing underlays different from unicast. They can follow a completely different topology. And the ECMP and fast reroute, all those technologies, techniques can be used for BIER as well. We started with the 4-bit string. Obviously, that's not practical at all. Typically, it's 256. But what if you have 1,000 edge routers in your network? How does that work? There are basically two ways to handle more routers than your bit string length. The first one is you partition all your BFERs into different sets. And that partition is done transparent to the overlay. It's completely handled by the BIER layer itself. For example, if you have 512 BFERs and your bit string length is 256, then you will have two sets. And then the BFIR, the ingress router, will send one copy for each set. Each set will have a set ID. And then the same bit number, say for example, bit number 1 will refer to BFER number 1, but the same bit in another copy, the second copy, will refer to BFER number 257. That is one way to handle the more BFERs than your bit string length. The other one is that you partition your large BIER domain into multiple smaller subdomains. For example, you have one subdomain for each IGP area, as an example, and then you only send one copy to all your BFERs in your local subdomain, and one of the BFERs could be area border routers between the areas, and that area border router will decapsulate incoming BIER packets, and then based on some overlay signaling, you will put on a different BIER header when it sends into the next subdomain. And then in a network, you may have multiple bit string lengths used at the same time. For example, you're transitioning your network from length 1 to length 2. Another important concept is BIER subdomain, which I alluded to just now. It's actually a very loose term. It can be viewed basically as a set of BIER routers for a purpose. And notice that the same set of BIER routers can belong to multiple subdomains. A subdomain can be for topology, in a multi-topology routing case, or could be a subset of BIER domains, or be a subset of a BIER topology, for example, an IGP area. It can also be a combination of the above. So now we have this tuple, subdomain, bit string length, and set. This tuple, the combination, each of the combination has its own BIFT, BIER forwarding table. Now, let's talk about BIER encapsulation in more details. We talk about that each BIER packet has a bit string, but there is more than just a bit string. We'll look at specific fields in the BIER header in the next slide. What I want to point out here is that the BIER header follows the outer encapsulation header, which could be MPLS, could be Ethernet, or could be any other encapsulation. This is a picture of the MPLS encapsulation. At the very top, you can see that there is a BIER label. That's a basic MPLS label entry. BIER label value 20-bit, followed by the transport class, bottom of stack indication, and the TTL. And then the real BIER header follows. The first is a 4-bit nibble with value 5, so that if some routers, transit routers, are doing ECMP hashing, they will not mistake this as an IP packet. So that's the purpose of that nibble. And there is a version number for BIER encapsulation, BSL, the bit string length, and entropy field that is used for ECMP hashing purpose. We have OAM bits. We have a diff serve code points, which serves the similar purpose as the transport class bits in the label entry, but this DSCP code points is used for non-MPLS encapsulation purpose. There is a protocol field, identifies the type of the payloads after this BIER header. And then there is a BFIR ID identifying the BFR that is sending this packet. And of course, then there is this bit string now, non-MPLS encapsulation is almost the same, except that instead of a BIER label there we have a BIFT ID. It's an opaque 20-bit number. I forgot to mention that here in the MPLS encapsulation case, the BIER label serves two purposes. The first one is to identify that after this BIER label entry, a BIER header follows. That's the first purpose. The second one is that this BIER label value will identify a subdomain, bitstring length, and set tuple, or we identify BIFT. Now, coming to the non-MPLS encapsulation case, it's almost the same, except that it's not a label, it's just a 20-bit opaque number, serves the purpose of identifying a BIFT that is used to forwarding this packet. But the outer encapsulation will identify that a BIER header follows. For example, if the outer encapsulation is Ethernet header, then either type AB37 will indicate that a BIER header follows this Ethernet header. Keep in mind that even with non-MPLS encapsulation, the payload of BIER that is after the BIER header could also be MPLS. IGP signaling or BGP signaling they're all similar. We talk about that each BFR, BFIR or BFER, they all have a non-zero BFR ID. And the transit BFRs, their BFR ID can be 0. Each BFR needs to advertise some labels so that the packet can carry that BIER label that indicates the BIF that is used for forwarding. So all this signaling is done similar. In this signaling here, I described here, I believe is for ISIS. Basically, for the BFR's loopback prefix, we attach this BIER sub-TLV that is used to advertise BIER information. It includes the subdomain ID and multi-topology ID and BFR ID, and also it can have some MPLS encapsulation sub-TLV or non-MPLS encapsulation sub-TLV that basically advertise the BIER label or the BIFT ID that corresponds to a BIER forwarding table. BGP signaling, very similar. I'm not going to talk about the details here. Coming back to the relationship between BIER and MPLS, we talked about already that we have a BIER label that indicates that the payloads after this BIER label is BIER, and it also identifies the BIF table, the BIF to use. So that's a BFR that is sending a BIER packet will impose a BIER label before the BIER header, and that BIER label is advertised by the downstream receiving BFR. And the receiving BFR will use this label in the packet to identify the BIF it should use to forward traffic. And then the BIER payloads could start with an MPLS label stack. For example, after the BIER header, the first thing you see is a VPN label. That's optional. And then the BIER packets itself can be transported on top of a base LSP. For example, you need to tunnel through or tunnel around a router that is not BIER capable. So in that case, we will have a tunnel label in front of the BIER label. But this tunnel label and VPN label, they are all optional depending on the situation. These are all generic MPLS functionalities I want to point out. And then BIER and segment routing. We talked about that BIER is the best multicast solution for SR because they have the same principle. They stick to the same principle of no per flow state inside the network. But we said that BIER is actually independent of SR. Here, the only relevance between the SR and BIER is that SR paths as well as non-SR tunnels can be used to tunnel BIER traffic between the non-adjacent BFRs. That's all. SR paths can be used for tunneling BIER packet. That's the only relevance between the two. And then, what about BIER and SRv6 or BIER, non-MPLS IPv6? You could have an IPv6 network that's not run MPLS at all. In that case, what's the solution? So there are two options here. The first one is what we call BIER in 6. It's a generic non-MPLS BIER that is applicable for to both IPv4 and IPv6. It's a generic layered architecture. It basically BIER over any transport, whether it's layer 2 or IPv4 tunneling or IPv6 tunneling, SR tunneling, non-SR tunneling, whatever. So that's one solution, what we call BIER in 6. And it is the IETF adopted solution. It is in the stage of working group last call. The next option is what we call BIER v6. It's also a non-MPLS encapsulation, but tightly coupled with SRv6. At this time, it's not a standard solution yet, but it is option available from some vendors. So BIER is a relatively new technology that was brought to IETF almost 9 years ago. So it's not that new anymore. We actually went through very quick standardization in IETF. We quickly standardized the BIER architecture and BIER encapsulation, ISIS and OSPF signaling. We also had RFC on underlay path calculation algorithms that you can use all kinds of constraints on algorithms that is different from your unicast routing. And we have the MVPN for BIER. MVPN as a BIER overlay, or you can say that it's a BIER as a provider tunnel for MVPN. And similarly, BIER as a provider tunnel for EVPN, that is in the IESG, the basic last stage before it becomes RFC. And we also have BGP signaling, and we talk about the BIER in 6, that is the generic non-MPLS BIER for IPv4, IPv6 network. And we also have quite a few drafts, internet drafts on brownfield deployments options. For example, BIER tether, BIER PHP. Tethering is basically you attach a BIER capable router, small BIER capable router to a large legacy router so that they can work together to handle BIER. BIER PHP is basically the penultimate hop pop of the BIER header so that the last hop does not need to understand the BIER encapsulation or BIER forwarding. That allows the last hop router to run BIER without having to understand the BIER or encapsulation or BIER forwarding. And we also have this draft called BIER Multicast as a Service, which is a cool way to enable multicast transportation or even BIER transportation at a global internet level, depending on how you determine where your replication points are. So we talk about all these wonderful things about BIER, and we talk about how BIER is the best technology for SR networking on the multicast sides. But why I didn't talk about 3 years ago. Unfortunately, we have this chicken egg dilemma here because it uses a new encapsulation and new forwarding algorithm. That means that you either have to have programmable ASICs, or you need to spin a new generation of those rigid pipeline-based ASIC. So because of that, even though the operators shown great interest when the BIER first came out, they had to back off because they realized that most of my deployed platforms won't be able to do this for quite a while. So when they back off, the vendors, they also hold back because they don't see a clear demand for the BIER feature. So we get into this dilemma. We do have some vendors have proof of concept or even production implementations, but the deployments has been lagging behind. However, the reason why I'm presenting this here now is because we are about to break this dilemma. The pioneer vendors, pioneer operators, they are working together. We are getting ready for the prime time deployment for BIER. The vendors have been doing the standardization work actively in IETF, as we talked about earlier. And they have also been working on hardware and software support. We actually now have the hardware capability across access, edge, aggregation, and core, across all those platforms from several major vendors, 3 or 4 several major vendors. So with that, with the pioneering vendors and operators working together, we are ready for the prime time deployment because this is the best technology. It handles scale, and it handles convergence. It is, technology-wise, it's just wonderful. And now we have the hardware capability, and we, as vendors and developing their software support, and the operators realize that, hey, I want to use this, and the vendors are actually having the product now. We are there for this deployment, for this technology. So that's basically my presentation here. Welcome questions, comments, either here or afterwards. I'm here for all 3 days. Happy to discuss any questions you may have now or offline later. Thank you.